Okay, great. Hi, everyone. Welcome to another webinar organized by ASPACS. ASPACS is Australian Pacific Conference on Combustions, and the 15th ASPAC will be in Singapore. So the registration is open now. It's one of the greatest events I've been involved in, attracting many researchers, many fantastic people from industry and academia, bring them together to share the latest innovation toward the challenges related to combustion, different aspects of these topics. So the early registration is open, and it's you have time until 10th of March. I just want to remind everyone, please ensure you're not missing the early bird registration time. So I'm very pleased to host this webinar. My name is Fatemeh Salehi. I'm Associate Professor and Academic Lead at Macquarie University in Sydney. My background is numerical combustion, and I'm working toward hydrogen safety. It's a great pleasure to have two great colleagues with me today, Professor Shaun and Dr. Hengrui Lee. So if you attended the previous webinar, you know about the structure, but I'm going to remind everyone, we will have the both talks first, and then at the end, we're going through the question and answers. Please post your question in Q&A session so I can see all of those, and we're going to cover all the questions at the end. So today webinar is about hydrogen safety, reliability, and application. I think you've already heard, if you attend the previous webinar, there have been two actually webinars related to hydrogen and hydrogen vectors such as ammonia, talking about basically hydrogen production and use of hydrogen in different sectors. If you're talking about hydrogen, is one of the great player or important player when it comes to decarbonization and transitioning from fossil fuel to renewable energies. So it's expected hydrogen contributes over $1 trillion to the economy by 2050 worldwide, which is fantastic. And to achieving these massive scaling targets across the board, safety and reliability are quite significant. So our first speaker, Associate Professor Shaun Chen, will focus on reliability and application, and the following talk by Dr. Hengrui will be focusing on hydrogen safe. So Professor Shaun is at University of New South Wales in Australia, Sydney in Australia. His research focuses on optical and laser-based imaging diagnostic for high pressure, high temperature engine environment. He also has expertise in technical, economic, and environmental analysis of energy system and fire safety. His research group has contributed to significant advancement in integrating hydrogen into the existing combustion system for cleaner, more efficient, and reliable combustion, demonstrating the economic and technical feasibility of hydrogen fuel power generation integrated with solar farm for baseload energy, renewable energy. So he in 2030, he was CSR International Hydrogen Fellow funded by Australian government. He managed significant research fund, over 20 million research funding projects. He supervised many PhD and master students, and he published over 100 high impact articles. So it's a great pleasure to have you here, Shaun. Thank you very much for joining us. So I'll now pass it to you for starting your talk. If you please share your screen, I'll leave it to you.
Right, Fatemeh, many thanks for your very kind introduction. Are you able to see my screen?
It's not in a presentation mode. If you please put it on a presentation mode.
Right. Just going to play around with it a bit.
You may click on display settings. Yeah, thank you.
Yep.
Perfect.
Oh, good.
Thank you.
Okay,
all
fantastic.
Good.
Right. Thanks, Fatemeh, for your very kind introduction. My name is Shaun Chen, and I work at the School of Mechanical and Manufacturing Engineering in University of New South Wales, which is located in Sydney, Australia. So before I start, I'd like to make a quick introduction to my school. It has a long history where it was established in 1949. Currently, the school has approximately 100 staff members and more than 2,500 students across various programs. We are consistently ranked as one of the top universities in School of Mechanical and Manufacturing Engineering, both in Australia as well as globally. We are a highly research-intensive school, attracting more than 11.5 million of research income, as well as publishing more than 400 research publications on an annual basis. Now, in terms of the group that I work with, I'm one of the co-leaders of the UNSW and Clean Energy Combustion Group, whereby along with two other colleagues of mine, Professor Shaun Cook and Professor Edward Hawkes, we work with more than 10 HDR students, as well as 3 postdocs tackling various aspects of the clean energy combustion. We have the capability to perform extremely fundamental level of research diagnostics, as well as practical level engine testings. In addition to that, we also have the capability to model a range of flame and using really fundamental tools such as direct numerical simulations, and also perform practical engine modeling using commercial software such as Converge. We collaborated with a range of industrial partners. Some of the work presented here today would be done in collaboration with them. So a quick moving on. So now I'm just going to talk about hydrogen after the brief introduction to the background. So hydrogen itself is highly attractive, and one of the main reasons is due to its carbon-free properties, as well as potential to be produced from a variety of renewable energy sources. Now, as a combustion fuel, hydrogen is somewhat attractive due to several properties such as its wide flammability limit, as well as high flame speed. This can potentially lead to short combustion duration, as well as the capability to operate under linear operation conditions, which can be used to enhance the efficiency of the engine process itself. However, hydrogen does have a couple of challenging properties, which makes it quite challenging when it comes to integrating it into engines for use. So if we were to use a more traditional method, such as pod fuel injection method, whereby the gas injection is injected during the intake stroke. So for those of you who are not quite familiar with the engine operation, this is essentially a video just demonstrating how the engine actually varies. In the case whereby you have the fuel and air being introduced into the intake pod, it will be entrained into the engine cylinder, whereby subsequently get compressed. And once the compressed reaches the designated timing, it will subsequently be spark ignited in this particular case, whereby the combustion gases are subsequently expelled from the engine itself. So this is just a very quick introduction to how an engine operates. In the case of hydrogen, and if it were to be introduced using a pod fuel injection, which is one of the most commonly used method, given that due to ease of implementation, as well as the lower requirement of the injection hardware itself, there are a couple of challenges that one would face. First and foremost, hydrogen actually has a very low volumetric energy content. And what this essentially means is that if the hydrogen were to be injected into the intake airstream, it's quite possible that we need to supply a significant amount just to meet the input energy requirement. If this were to happen, the hydrogen could potentially restrict the air that could eventually be drawn into the engine itself, leading to that air displacement issue. Now, in addition to that, if we were to be using pod fuel injection, what this basically implies is that the hydrogen has to be introduced during the intake stroke, and there will be some energy or work that needs to be done in order to compress the fuel itself during the compression stroke, so which would also impact the efficiency of the engine operation itself. Now, there are also a couple of safety concerns. Hydrogen has a low minimum ignition energy. If you were to look at the table, it's approximately an order of magnitude lesser than what you typically face when it comes to the more conventional fuels. And what this means is that if we were to use a fuel introduction method whereby it's introduced during the intake stroke, this leads to hydrogen having a very long residence time within the engine cylinder itself, potentially exposing it to different hotspots or deposits within the engine cylinder itself, leading to the possible occurrence of pre-ignition, ignition before the designated timing. And on top of that, hydrogen does have a very short quenching distance as well as a high flame speed. So in the event whereby the combustion event does occur within the engine cylinder itself, and then the valves are not properly seated, it's possible that the combustion will propagate all the way back to the point of introduction, which is located external to the engine cylinder in this particular case. So these are the occurrence of the pre-ignition as well as the backfiring and other phenomena such as knocking could all potentially impact on the engine operation, and in the more severe cases, causing significant damage to the engine itself. So these are the number of challenges that one has to face when we're trying to integrate the hydrogen into internal combustion engine. Now, given all these different types of challenges, one of the potential approach that can be used to overcome some of the listed challenges here is through the use of direct injection method combined with late injection timing. Now, direct injection, as its name implies, involves the direct injection of the fuel into the engine cylinder itself. So if we were to do this at a comparatively late injection timing, this will ultimately reduce the residence time of the hydrogen within the engine cylinder itself, potentially reducing its exposure to hotspots and deposits, and thereby reducing the pre-ignition risk. Now, in addition to that, given that the hydrogen is now directly injected into the engine cylinder, this will ultimately mitigate the air displacement issues, such as described when it comes to the pod fuel injection method. Given that the hydrogen is now introduced into the cylinder directly, there's no backfire risk in the sense that the fire would now propagate back to its point of introduction, which is located within the engine cylinder itself. And last but not least, the late injection strategy combined with the direct injection method could be used to manage the compression work that's required to be done to compress the fuel. And this also opens up different pathways when it comes to the optimization of the performance of the engine, such as the redirection of the injector or reorientation of the injector just to enhance the performance of the engine itself. So these are the benefits associated with the use of direct injection strategy when it comes to hydrogen, the integration of hydrogen into engines. Now, despite addressing many of the challenges through the use of direct injection, the hydrogen itself still has a pretty challenging property, which is its high auto-ignition temperature that's considerably higher than some of the conventional fuels. And what this basically means is that in the event if we were to just directly inject the hydrogen into the engine, it would not be easy to compress and ignite it unless we do something that's highly, make some modifications to the engine itself. So a lot of the research groups, including my own research group, we have looked into the use of alternative method just to assist with the ignition of the hydrogen jet itself. Some of the methods would include the usage of spark plug, glow plug, or in our group's case, we would favor the pilot diesel method due to the competitive advantages that it offers. Now, the pilot diesel can be used to create a high temperature environment to facilitate the ignition of the hydrogen jet itself. The advantage of this method is that it's possible for it to create multiple ignition sites within the engine cylinder itself, and thereby providing a more robust ignition performance. Now, in addition to that, given that we are using pilot diesel to ignite the fuel, it's also possible for us to also increase the energy share that's coming from the diesel itself in the event whereby we just increase the contribution coming from the diesel itself should the operation itself requires it, and thereby providing the system and this additional layer of robustness to handle the different type of the operation requirements that one may face during, depending on the sectors that you're working in. Now, one of the challenges of implementing this method in the past is that there's a severely lack of database concerning the behavior of the highly pressurized hydrogen jet, as well as the dual fuel combustion process under engine relevant conditions. Fortunately, this has been addressed to a certain degree through many of the recent publications, including some of the findings that will be shared in the subsequent slides. And one thing to note is that today I'll be focusing mainly on addressing some of the in-cylinder combustion processes that we're observing. And there are still many other different challenges that needs addressing before the hydrogen can be fully integrated into internal combustion engines. for mobile applications. For example, challenges such as the hydrogen storage system itself, as well as the hydrogen embrittlement issue. All these are extremely important, and we are aware of there are multiple different efforts that are dedicated towards addressing these specific problems, but this is currently beyond the scope of what our group is working on at the moment. So before we go into the technical details, sometimes it's worthwhile just looking back into what we could potentially achieve if the technologies were to implemented to its full extent. So our group has performed this engine testing at the University of New South Wales, implementing the hydrogen diesel dual fuel direct injection technique. And with this, the demonstration, which was conducted in a compression ignition engine with varied bore sizes ranging from 50 up to 100 millimeter. And with our recent test, we were able to demonstrate that using this technology, we can achieve a high energy substitution up to 90%. So in other words, for hydrogen. So in other words, 90% of the energy in this case is actually coming from the hydrogen, with the remaining 10% coming from the pilot diesel. So one thing of note is that this does not represent an upper limit of the technology itself, rather is an indication or is mainly arising from the limitation of the injection hardware that we are using. And there's no reason why we can't go further than what is being currently demonstrated. Now, with this 90%, it's approximately 2 times greater than what has been previously reported in the literature when it comes to the usage of hydrogen port fuel injection, whereby a typical upper limit of 30 to 40% has been observed over a comparative range. Now, given this high energy substitution, we will also observe a significant reduction in terms of the carbon dioxide emission, as well as an increase in the indicated efficiency as compared with the diesel baseline, which is probably attributed to these highly favorable combustion properties of hydrogen. Now, with hydrogen, one of the main concerns would be NOx emission, and indeed, with certain injection strategies, we do observe an elevated level of NOx emission, going up to 3 times as compared to what we observe when it comes to diesel baseline. But as what we have demonstrated also in our studies, with slight adjustment, if the injection timing variation, as well as the usage of other strategies, it's quite possible for us to maintain an efficiency as well as a NOx emission that's comparable to that of the diesel baseline, while retaining the significant carbon dioxide emission reduction ability of the technology itself, so making it highly attractive for use. Now, when it comes to conventional fuel, the fuel ignition is basically mainly triggered through the compression within the cylinder itself, whereby the occurrence of the ignition is largely dictated by the fuel type, the timing at which the fuel is being introduced, as well as the engine parameters itself. Now, when it comes to dual fuel compression ignition engine, given that we are introducing this additional fuel into the system, and sometimes with the use of a separate injector, this basically opens up a variety of parameters that we have to control, adding a layer of complexity to a certain degree, but also providing us with this opportunity to optimize the engine performance even further than what we were able to achieve when it comes to the conventional compression ignition engine. Some of the parameters that now becomes variable would include the timing and injection sequence. So when do we introduce the fuel relative to one another, and in what sequence should we be introducing the fuel? The injection duration, as you can imagine, through the variation of injection duration, we can actually change the energy share that's coming on from each of the fuel, which is one of the most important characteristics of this specific technology, something that I'll be discussing in detail in the subsequent slides. The jet interaction angle would be important as well when it comes to dual fuel combustion, given that the hydrogen in this case does not ignite on itself, and its ignition is largely reliant on the contact between the pilot diesel with the hydrogen itself. So all these are different parameters that can influence the performance of the combustion performance of the dual fuel process. So I'm going to go through some of the some of the data that we acquired in our laboratory. And before I do that, I think it would be a good idea just to give a brief introduction into some of the techniques that we're using. So what you see here is the constant volume combustion chamber that's optically accessible. This chamber can generate the high temperature and pressure condition that one typically experiences expect to experience in the model engine range. And the jet fuel of interest in this case will subsequently be injected into this high temperature and pressure conditions that have been simulated within the chamber itself. The technique that we're using here is something that's known as Schinderian imaging. So it's essentially comprised based upon the use of introduction of a parallel light rays through the use of a series of optics, which are subsequently directed through the combustion volume chamber before the parallel lights are eventually projected onto the high-speed camera itself. When the fuel gets injected into the chamber, the high-speed jet prior to the ignition, we can actually trace the perturbation that it introduces to the background signal to understand how the jet is actually developing. And on top of that, when the combustion does occur, this will lead to the generation of gases of different density as compared to the background. So the presence of the density gradient will subsequently lead to the deflection of the parallel light away from its original light array. And you can naturally imagine that this would manifest itself in the form of dark contrast when it's captured on the image. So if we were to study the evolution of the dark contrast region itself, this would tell us where the ignition occur, and more importantly, how far does it actually stabilize away from the injector itself. So something that is commonly observed when more conventional fuels are used. And in addition to that, we are also tracing the heat that's being released during the combustion process. So what you're seeing at the bottom are basically the heat released at different stages of the combustion. We typically see a much higher heat being generated during the premix combustion phase, which is corresponding to the readily ignitable fuel mixture at the timing of ignition, whereas the heat release during the quasi-steady state is indicative of the heat release during the diffusion combustion phase. So when it comes to the studying of dual fuel combustion, we are essentially injecting both the diesel as well as the hydrogen into the same hot environment. But in this case, we are introducing two fuels rather than one. So if you look at the video that we acquire, in this case, the hydrogen comes into contact with the diesel that's injected at a slight angle with respect to the horizontal axis. And upon contact, you see that the flame subsequently propagating throughout the jet. And more importantly, what's interesting to note here is that the combustion actually propagates all the way back onto the nozzle itself, which is something that's different to what is typically observed when it comes to the more conventional fuel. What this perhaps suggests to us that this propagation of the flame back to the nozzle during the injection period is that there will be a stronger, higher heat transfer from the hydrogen flame back onto the nozzle itself. This is perhaps something that we have to bear in mind when we are running the engine using this specific technology, because this increased heat transfer could potentially have an impact on the injector durability. So something that we need to assess. Now, the dual fuel process in the past has predominantly been done in most of the work that's been done in the past. Most of the research groups had focused on maximizing the energy output from the clean fuel itself, whilst minimizing the energy input from the pilot diesel, which is more carbon intensive. And this has led to a relatively a paucity of data looking into how this, when we try to maximize the situation whereby we are trying to maximize the energy coming from these alternatives from the pilot diesel source itself. And there used to be a lack of data, but this has been addressed through some of the recent research efforts, some of the findings which I'll be sharing in the subsequent slide. So for this specific set of experiment, we have conducted it into in the controlled constant volume combustion chamber. In this particular case, we have fixed the total input energy into the chamber while varying the energy share that's coming from each of the fuel. One thing of note is that given that we know that there are different types of parameters that could potentially impact on the performance of the combustion processes itself, it's important for us to minimize as much of the effect of these other parameters as much as possible. So in this particular case, we have maintained a converging configuration whilst ensuring that they are using a near simultaneous injection strategy. We have conducted the experiment over a range of oxygen concentration, but in the interest of time, I will be only presenting the result that were acquired under 21% oxygen concentration. For comparison, we have also acquired some reference cases, which in other words, the single fuel injection cases under similar condition, just for cross comparison. So all these cases are conducted under an ambient condition with 5.2 megapascal, as well as an ambient core temperature of 890 Kelvin. For ease of reference, we have come up with the following acronyms, whereby the numerical numbers after each of the letters will be indicative the energy share coming from the different fuels. H90D10, for example, would be indicative a case whereby the energy share coming from the hydrogen would be 90% and 10%, with the remaining 10% coming from the diesel itself. Now, what you see here are the shielding images, as well as the apparent heat release rate profile coming from each of the cases. The cases that are locating at the top would correspond to the case whereby most of the energy share is coming from the hydrogen, whereas the image that's located at the bottom would correspond to the case whereby most of the energy in this case would actually be coming from the diesel itself. And all these experiments were conducted under an ambient condition of 21% oxygen concentration. So just if we were to look at the shielding videos that have been captured, what would be interesting to note is that under the conditions that which we produce the data, all the hydrogen, all the diesel will actually ignite externally to that of the hydrogen jet. So what this basically implies that under the configuration as well as the ambient conditions that we have selected, the diesel jet itself will not actually, the ignition of the diesel jet will not be impacted by the presence of the hydrogen jet itself. And one thing of note is that what you can see from the images is that under the conditions whereby a majority of the energy is coming from the diesel, you actually see a lot more luminosity, which is typically indicative of the presence of soot. And this is something to be expected given the carbon intensiveness of the diesel jet itself. So if we were to analyze this on a frame-by-frame basis, so instead of just looking at the videos, what we're going to do here is just going to be looking at the frames. So again, the shielding images presented at the top correspond to the case whereby a majority of the energy share actually comes from the hydrogen, whereas the case at the bottom, a majority of the energy share actually comes from the diesel. The shielding images shared from the left to right will correspond to those frames that is acquired as a function of time after the start of injection. The blue line here is indicative of the boundary of the non-reactive hydrogen jet. The red line here is indicative of the boundary of the pilot diesel jet in this particular case. And then the green line here is indicative, correspond to the boundary of the reactive cases. And the yellow, and what you see on the top are the images that are captured for the dual fuel cases, whereas what you see at the bottom are the single fuel references that are injected into the same condition as that of the dual fuel cases, but without the presence of the hydrogen. So the yellow boundary that you see at the top is pretty much an overlay of the boundary of the single fuel reference on the dual fuel cases, just to ease visual comparison. So if we were to look at the images, the one that's selected for more detailed analysis, one thing that will become interesting is that in the case of the single fuel injection, you see the formation of this luminous zone at the head of the jet, and which gradually diminishes over time. Whereas in the case of the dual fuel cases, the interaction of the diesel jet and as well as with the hydrogen jet would actually inhibit, reduce the amount of luminosity that can be detected. So this suggests that the interaction of both jets could actually have an impact on the combustion as well as the soot processes itself. Now, in addition, if we were to focus on the data that have been, the measurements that we collected for the cases whereby a majority of the energy is coming from the diesel itself, in this case, there are also a couple of interesting features. One of them being that in the case of the dual fuel cases, if we were to compare the distribution of the soot relative to the single fuel reference, you see that the soot zone in this particular case will be, the axial length of the soot zone will actually be prolonged. And in addition to that, we are also seeing some interesting features being formed at the upper boundary of the jet itself. So if we were to play the video that we acquired this case, and if we were to focus on the zone, this zone that's located right below the Sion arc, what you see here is that upon the occurrence of the ignition, there will be an outward counter-rotating region that's formed with certain luminosity that gradually diminishes as the flow structure moves downstream along with the jet itself. This is something that's simply unobserved when it comes to the single field reference. And this is also something that's not observed on every single run, but the frequency is comparatively high. And the frequency does change as the ambient oxygen concentration changes as well. So the frequency of detection actually diminishes as the ambient oxygen concentration drop. So all these are demonstration of how these dual field processes could potentially impact on the mixing as well as the combustion processes of the dual jet, and something that we should pay attention to when it comes to using them in the engine itself. I'm just going to go through one last set of results prior to ending my presentation. So in this case, a series of measurements that have been collected for the different cases, whereby we have the, on the left, you have all these measurements that are conducted whereby a significant of the energy share is coming from the hydrogen. And at the other end of the spectrum, this is a case whereby a significant of the energy is indeed coming from the diesel itself. The first row would correspond to the heat release rate. So this gives you an indication of the heat release at different stages of the combustion. The second row corresponds to the normalized heat release. So this is basically the heat release integrated as a function of time divided by the total energy input into the system itself. The third row corresponds to so a value that's closer to 1 would indicate a highly effective, efficient combustion process, whereas a value that's closer to 0 would indicate an ineffective, inefficient combustion process. Intensity in this particular case corresponds, measures the luminosity that's coming from the flame. A higher value is typically indicative of the presence of greater amount of soot, and vice versa. And last but not least, we also track the evolution of the flame base, seeing how much is stabilized with respect to the nozzle. Now, one thing that's interesting is that if we were to look at the dual field versus the single field reference, what we see here is that the dual field process is actually a lot more efficient than the single field reference. This is not totally unexpected, given that the injection settings that we have selected to generate the pilot diesel jet is not exactly selected to optimize the combustion of the diesel. Rather, it's just simply selected to ensure that this consistent delivery of small amount of diesel just to assist with the ignition of the hydrogen jet. With the presence of the hydrogen itself, this lead to ensure that the heat release from the diesel itself is pretty efficient, even though the settings that we selected may not necessarily be the most optimized. And in addition to that, we are showing that there's a corresponding decrease in the luminosity of the dual field cases as compared to the single field references, which is consistent with our Schiller-Rein observation. If we go to the other end of the spectrum, we'll see that the normalized heat release from the dual field cases would be slightly lesser in the case whereby the energy output, the energy is mainly supplied by the diesel, which is to be expected given the unoptimized setting. When it comes to photodiode, what is interesting to note here is that the intensity from the dual field cases are comparatively lower than what is typically observed on the single field references. This is despite the prolonging of the extension of the soot zone as well as the formation of the recirculatory zone. So these are the interesting features that we are observing. So just a final quick 2 notes. I know my time is up. So there are many questions on how this technology could potentially offer the most competitive advantage. One of the sectors that we see that it could potentially be applied would be for the use of electricity generation. There's an increasing energy penetration of renewable energy into the grid in Australia, and many of these renewable energy resources are highly intermittent. Their production is highly dependent on the weather as well as the time of the day. This has led to the destabilization of the grid, necessitating some corrective actions such as curtailment. Whilst curtailment is highly effective, in essence, it's also lead to some kind of loss for the plant operators itself. With the use of the hydrogen to diesel technology, what this could potentially do is that in the case whereby you have excess energy, the energy can be actually be stored as hydrogen. And the hydrogen engine now offers a pathway at which this gas could potentially be converted back into energy again, just to assist with the grid stabilization, just assist with the stabilization of the grid, especially when there's a mismatch between the demand as well as the supply. And last but not least, this could potentially be used to assist with the hydrogen export as well. So Australian national strategy is basically targeting a global leadership in both production and export by 2030. And in order to achieve that, it's actually important for us to be able to find a cost-effective long-distance hydrogen transport solution. One of the issues that we face when we are transporting liquefied hydrogen is the occurrence of void-off. So in other words, some of the liquefied hydrogen actually gets converted into gas during the transportation process. And this can lead to an over-pressurization scenario, presenting a safety risk. And in most cases, the hydrogen has to be vent off just to maintain the pressure. And this represents a safety concern, another safety concern. With the hydrogen diesel fuel technology, there's a possibility at which this hydrogen, boiled hydrogen, can be used to fuel the motion of the ship itself, and therefore changing the transport economics. These are just a series of publications that were made in this field, but more importantly, I would like to end my presentation by thanking all the contributions from my colleagues, past and present students, past and present collaborators, and more importantly, the funding agencies. Without their financial support, none of this work would be possible. Thank you.
Thank you very much, Shaun. I appreciate it. It was an excellent presentation, and I've learned a lot. Well, we cover about hydrogen application and also the reliability challenges, particularly when it comes to hydrogen combustion. Now we're moving to our next speaker, Dr. Hengrui. So before introducing him, I want to remind everyone, please submit your question through Q&A. We try to cover them as much as possible at the end. So Dr. Liu is currently working at Fahrenheit Global as a fire engineering consultant, where he applies both engineering principles and computation analysis to develop practical fire safety solutions. So his work focuses on protecting critical infrastructure, ensuring regulatory compliance across various industries, and addressing energy challenges and safety challenges in new energy assets such as hydrogen facilities and storage. So he completed his PhD in mechanical engineering at the University of New South Wales, Sydney, Australia, where his research focused on advancing fire suppression system and risk mitigation strategies through computational multi-phase flow techniques. He also worked as a research fellow at both UNSW and Macquarie University, focusing on both numerical techniques and experimental validation. His research also contributed to hydrogen safety, utilizing both experimental investigation and numerical simulation to assess fire and explosion risks associated with hydrogen. So now I'm passing it to you, Henry. So his talk's focusing, as I said, on hydrogen safety, and he's going to present a few case studies relevant to hydrogen safety and reliability. Over to you, Henry.
Thank you, Fatemeh. Thank you for your kind introduction. And I just want to make sure that everyone sees my screen as it is, the presentation slide. And if I click on the presentation mode, I hope it's full screen right now.
Oh, good.
And thank you, guys. And I shall start my presentation. Thank you for invitation. And it's really a great honor to be presented in the Asia Pacific Conference on the Combustion pre-webinar. And as Fatemeh have introduced, I am by now working in a fire engineering consultancy as a fire engineer. And I have the pleasure of having my research done in hydrogen safety in most collaboration with Macquarie University. So today my topic will be computational insights towards hydrogen safety. And let's get started. So a bit of an outline of a series of experimental and numerical results that we obtained. We conducted in collaboration with many researchers around the world. Macquarie being the main collaborator, and we collaborated with University of Tasmania on fundamentals by experimental and numerical approach. This is our foundation. So we lay our numerical bricks on the foundation of experiments, which we will go through later on. And then we expand a bit on machine learning. We have we have tried to expand our knowledge and our databases to make some more faster predictions on machine learning. And that research has been collaborated with University of Michigan in America. And then we moved forward basically to, in apply our technology and our knowledge from the CFD modeling to a larger scale application and more specialized applications, which is liquid hydrogen refueling station. This is purely done within Macquarie. And a bit of myself, I think it's too much already. And I've done my PhD in UNSW, very pleasured, honored. And I'm right now a fire engineering consultant at Fire Global. We are a fire engineering consultancy company, and we're more looking into compliance and real-world fire engineering problems. And definitely hydrogen will be, in the future, one of the things we need to look into, we need to pay more attention to. So that's why we are here to explore things that's why research is made as a research, right? And without further ado, let's go into the main topic today. Hydrogen, as we know, is receiving increased awareness in each part of the world research industry as a potential field, because we are trying to decarbonize as a clean energy, because as Shaun previously just demonstrated very greatly, we want to basically reduce our carbon footprint as low as possible. And so it also have a great potential as an energy carrier, because it provides a lot more energy. However, we must notice that hydrogen have its limitation right now because of its its safety risks, because it's so explosive and it's so light dispersive, and also the property of hydrogen is significantly different compared to the traditional fuels as well. So that basically we have a lot of unknowns in front of us need to be explored. So there is definitely a demand and a predicate of a fast and accurate assessment of hydrogen safety risks, especially when we are wondering if they are leaking or we do. So as I said, experiments lays our foundation for our numerical blocks. So our experiments are conducted in Macquarie with the Macquarie dispersion chamber. And this is basically you're looking at a schematic of the chamber. We have a PC to log the data. We have a data logger. We have gas sensors, which measures the temperature, gas concentration, etc., for hydrogen, helium, all sorts of gas that you can think of. And basically, we are attaching them to the side and the top on the chamber, this chamber itself. And we are currently using a helium tank. Basically, we're using helium as a surrogate of hydrogen in consideration of the safety factors, which we will talk about later on as well, whether or not helium is a good surrogate of hydrogen. And we basically inject our gas here and we let it disperse. And we have a capacity of adjusting the lab to make a slope, basically in a tunnel scenario or in a chamber scenario, have a bit of slope. And we have a capacity as well. Sorry, I may not get my laser. Right. We have also the capacity of introducing a wind to model basically how to simulate basically a natural ventilation condition or mechanically ventilated condition. So this is basically a photo of what you've just seen in the sketch. We have sensors, as we said, attached on the side of the walls and top of the walls. We have a nozzle connected to the flow regulator and connected to the tank as well. So here is basically the adjustable leg. We can use that to create a slope. And with opening, whether or not we attach it to a fan, we can create a natural ventilation or forced ventilation scenario. And we've been using this experimental rig, the Macquarie chamber, a lot. That's basically formed our foundation for the next few projects. First thing first, I'm a CFD guy, computational fluid dynamics. And most of our CFD analysis here I'm going to present today are done in cooperation with Flex and with Sketchcom. So Flex is the software we're using, and it's specialized for hydrogen dispersion and explosion, and for other field as well, dispersion and explosion. It's developed by Sketchcom. And its beauty is that it's very easy to use, and they have a porosity distributed resistant concept. So basically means that you don't have to worry too much about your mesh generation and things like that. basically what it does is on the intersection or on the interface of fluid and solid of our obstruction, it makes a portion of that cell being accessible or inaccessible, being the porosity, we call it here. And it's also having the ability of using simple K epsilon RAS model to having it computed more efficiently and suitable for this case as well. And we are also using NCI Gaudi as our computational platform. So it's a HPC platform governed by Australian government, and we should be able to deploy and run large parallel simulations on it. And it's basically having the beauty of fast simulations coming in. And to, as always, we need to validate our simulation. And by validating our simulation, we use our experimental studies like we just said before. And as we said, helium use, and we are using a pure dispersion scenario, basically meaning we don't have any slope. We don't have any fan attached to the side. And so the helium or hydrogen, the gas is injected from the nozzle here up here, and we let them disperse naturally. So we are using this very basic scenario as our validation. And we all, as we see from the results here, surprisingly, or actually not surprisingly, the experimental data or the numerical data actually agrees very well with the experiments. We are having our error controlled within 10% in most cases. And this is exciting news, basically means that our model works and our model would predict the flow scenario pretty accurately. And the beautiful thing about CFD is that we can visualize and we can obtain a lot of things that we cannot easily see in experimental studies. For example, this one is, as I said, the validation case study, the pure dispersion study. And we can see as time goes by, I'm cutting the gas concentration as 4%, because that's 4% is what we know as the lower flammability limit of hydrogen. So when we basically see the gas concentration above 4%, we know it's a dangerous zone, and it have a potential of ignition and have a potential explosion as well. So we see how the dispersion goes and how does the dangerous layer or critical layer drops down and how it gets stabilized in such a scenario. So 2.5 seconds, it's just starting to disperse. 10 seconds, it's basically dispersing around. 50 seconds, it's already stabilized. 100 seconds, you don't really see too much of a difference. And we can also see at different height as well, different location of the cross section, when does it reach to that 4% critical line. Validation study, and we, as I said, having the beauty of CFD study, we can visualize a lot of things that we cannot. And as we do not really expect that the ventilated case study here actually showed not very symmetrical behavior in terms of the critical layers or in terms of how much of the chamber has been occupied by the chamber. Right, so if we go to the next one, we have this ventilated case study as well. We have, I'm just presenting a small ventilation velocity, and we can see whether or not the dangerous zones or dangerous gas has been successfully purged from the chamber itself. So we see that if we have not enough velocity or not enough ventilation, we will have the second half of the tunnel or the later half of the tunnel being still in danger, so it's a failed purge scenario. Similar things here. So if we model the slope condition, if we have slightly tilted the tunnel or the chamber, this is what it will look like. So that's our basis or starting point of the study. And during this study and during our own study as well, there are many questions asked. The main question is, how different is what is helium a good surrogate of hydrogen? What's basically the difference in between them in terms of modeling and in terms of experiments, in terms of the dispersion? Will that be critically different? So as we see, hydrogen and the helium basically differs in their density, and the diffusivity is their major difference. So we did a numerical comparison as well, adopting three methods: equal volume, and equal concentration, and equal buoyancy, by just cleverly, smartly, just adjusting this n number exponential. So we can compare the differences between helium and hydrogen. So here we have, as you see, in a pure dispersion scenario, hydrogen and helium doesn't really seem to have too much of a difference. In a ventilation scenario, you do see some of the difference here, that especially in different ventilation conditions. And probably in a lower condition, you don't really see a difference, but in a bit of higher velocity condition, you don't really see too much of a difference. But a lower velocity condition, due to the much higher diffusivity of hydrogen, you will see a much more higher concentration field upstream as well. And compared method A and B and C, basically equal concentration, equal buoyancy, and equal volume flow rate, we find that in most cases, the method B, which is equal volumetric flow rate, is the better one that you should probably choose. But A and C works better compared to B if you are looking for some specialized cases, or if you are concerning about now the beginning of the hydrogen dispersion or the gas dispersion, or if you are actually looking at plume shape or concentration, C is more important, or basically giving you a better presentation. And we further expanded our study. So we all know that even CFD studies give you a bit of a fast track, or give you a bit of a more potential in accessing more data, but still they consume time, they consume many computational resources, they require more experiences. So there is actually a need for more fast predictive models, and we need a lot more data compared to what we can gain from experiment and CFD studies. So we introduced the method of machine learning, and we have data-driven models coming into play to help us expand the database or the data region we can play around with, and potentially as well to give us a bit of a fast predictions to give us some insight on the potential scenarios. So we are having a low fidelity data model and high fidelity model. So we, as I said, the foundation experiment. So we consider the experimental study or experimental data as high fidelity, simulation as low fidelity. And we are using this model basically to combine them, to merge, fuse all this data together, and to optimize the training method, or to optimize our model to obtain a good prediction using a fuse of low fidelity and high fidelity data. And our aim is to use this data set to try to predict high fidelity data as well. So in some cases, we don't have this simulation run, we don't have this experimental done, but we want to see this insight. Can we predict that from this machine learning model? Answer is yes, it's working great in some of the scenarios, definitely. And as you see from the bottom side, we're showing the prediction, and basically it's agreeing pretty well with both high fidelity and low fidelity data. It's making good predictions, especially when we are away from the injection point, which we don't really expect too much of a high fluctuation of the gas concentration, or we don't really expect too much of a high change in gradient. So around these points, we have a good prediction from the model. However, as model is a model, it has some limitation on itself, like I said, mainly because of the gradient change and the fluctuation. we may experience a bit of an inaccurate. So you see the fluctuations there, or the uncertainty here in between the prediction and actual models, but it's still in a very good condition. We still have room to improve though, but it's giving us a very good indication of insight already. And to give you an idea whether or not we are worth it to go forward, it's not really worth it to do experiment or to do simulations. And lastly, we expanded our study to more real-life scenario and to especially and to the scenarios that are very challenging to actually do experiments on. And surprisingly, we're using the same picture, this hydrogen carrying tank on this ship. So we are having a problem of liquid hydrogen, which is cryogenic as well. How does liquid hydrogen in cryogenic conditions or in low temperature conditions, what if they leak? How does this disperse? How does this affect the overall safety and risk of the refueling station or the storages themselves? So a bit of a simple scenario, we have considered the leakage from different directions from the tank. We also have basically considered different wind conditions coming from different directions. As we said, as well, validation study. And our validation studies show that our numerical model predicts reasonably good, giving us reasonably good insights in terms of the behavior, the dense gas behavior. And some simulations done here. So we see that if we have the wind direction coming with the hydrogen leakage direction, we probably will see it's been contained, although we would probably expect the leak out from the barrier, but it's not really endangering too much of the other area surrounding the refueling station, so it's more contained within this barrier. But if we have actually a perpendicular wind coming through, we find a much higher leakage, or we find a much higher spill, let's say around, it goes past by this barrier, so it's endangered us. We didn't really expect that to happen, a bit of a surprising. So this is where the CFD can really play its beauty on. When we designing for these real application scenarios, we don't really have to go through the expensive or even sometimes unrealistic experimental studies. It gives us insights in terms of how we guide our designs to be more safe. And that's pretty much the end of my presentation. I would take this chance to wrap up on what insight we've gained by these computational studies and experimental studies. Experiments are important. As I said, they lay foundations. They give you an anchor point to know whether or not we are heading towards a right direction. But expanding from there, CFD offers us great advantage in terms of accessing data, visualizing data, seeing things measures that we cannot really see easily in experiments. Much safer, much easier, especially when hydrogen safety is a huge concern. I know that Fatemeh is pushing hard to really run hydrogen into the dispersion chamber, but we still have too many challenges. CFD is much safer. Large-scale specialized purpose, like I said, we cannot really use even easily the pressurized, liquidized liquid hydrogen, which is more dangerous. So these concerns we don't have this problem in computer world anyway. And we have machine learning coming into play as well to expand our data set and to help us make quick decisions, to give us quick insights, to give us directions on whether or not we further investigate into that. So, but keep in mind, garbage in, garbage out as a golden rule for simulation world. And we should be always taking care in developing the models, not really blindly trusting this. And hopefully we should be able to, publications, don't worry about them too much, it's just for courtesy. Hopefully we can engineer a better world, and hopefully our skills and knowledge can be transformed or can be applied into real world scenarios and to guide our production and to guide our real world lives in a much more effective way as well. That's some insight that I gained in industry. So thank you guys for your time and for your patience to hear. It's a long night. Thank you.
Thank you very much, Henry. I appreciate it. Thank you to our both speakers. It was fantastic to learn about this amazing research. We have a few minutes. I try to go through the question already submitted. I think I start with you, Shaun. The first question is asking about your views on the use of hydrogen to clean carbon deposit of internal combustion engine.
Right. Thanks, Muhammad, for the very interesting question. We do observe that when we are using hydrogen alongside with diesel, we do not quite observe as much carbon deposits onto our piston after the engine operation. So I think that there's some potential there for that to occur.
Okay, thank you. And the second question, have you tried higher injection pressure level as 52 bar?
All right, I think there's some confusion there. So the 5.2 megapascal that I referred to is the ambient condition at which we injected the hydrogen into. In terms of the actual injection pressure of the hydrogen, we were running it over a range of injection pressure going from 100 bar all the way up to 300 bar. So we are running it at the higher end of the injection pressure spectrum when it comes to gas injector.
Thanks, Shaun. The next question is for you. How did you determine the high hydrogen concentrations cause brittleness in the engine material? Would this not void the engine warranty?
Yes, so the hydrogen embrittlement is definitely an issue that needs looking into, which is a bit beyond the scope of what I'm investigating. But there are many researchers that are done in this area. And I would say that any modification to the engine without the engine manufacturer's approval would naturally attract some issue. So what we are trying to demonstrate here is the potential of the technology itself rather than tackling the specific warranty issue associated with each of the engines.
I think the next question is also related to materials of engine. Will continental injection of a small amount of hydrogen to engine damage the materials of engine?
Yes, I think with the hydrogen usage, definitely we need to assess its impact on the engine material on the long run basis, and the degree of damage or not is really dependent upon the operating conditions of the engine and the actual material use. So we have to assess it on the case-by-case basis.
Okay, thank you. I'm not sure if you can give the answer from top of your head to the next question, but I will read it anyway. What is the resulting life cycle carbon intensity in terms of the kilogram CO2 per kilowatt of hydrogen combustion in an internal combustion vehicles compared to hydrogen fuel cell vehicles? Basically, which one is better?
All right. Well, excellent question, and you are indeed correct, Fatemeh. I can't answer it off the top of my head without performing the specific analysis for the scenario at hand. But I will make the comment that when we are comparing fuel cell to internal combustion engine, there are some similarities in terms of the upstream processes because they would most likely be using the same, and we still need to take the consideration into the storage issue as well. In addition to the carbon intensity of the specific equipment and also the operation that you're talking about, we also have to think about there are other things, factors that come into play. One of which would be the sustainability, right? So when it comes to internal combustion engine, it's typically made of common metals. They're highly recyclable. When it comes to fuel cell engines, then we have to start taking into consideration whether that is indeed the case. In addition to that, there are other issues such as in the case of fuel cell, is highly susceptible to any impurities in the hydrogen itself, whereas hydrogen in internal combustion engine, the usage is pretty robust. And last but not least, the fuel cells cannot be used in the highly vibrate environment with a lot of vibration, such as mining sectors, for example, whereas internal combustion engine would not present an issue. So these are all the different type of considerations that one has to make in addition to the carbon intensity, which is of course important, but ultimately the choice is really specific to ultimately the application that one might be looking at.
Exactly. And of course, it depends on application and also transition. So hydrogen combustion is very important for transition. And it also depends on what application we're targeting. So the next question is actually about DNS simulation and the number of reactions considering kinetic model. And do you still need to model turbulence chemistry in your numerical simulation?
All right. Personally, I'm more into the experimenter, so I would have to direct this question to my colleague, Professor Edward Hawks, and I'm pretty certain that one of his recent PhD graduate has performed direct numerical simulation involving diesel and hydrogen environment. We do have a couple of collaborations with other institutes as well, such as Fatemeh, and as well as Lund and as well as DTU. They are all using LES and other tools to simulate what some of the phenomena that you're observing here. So it's definitely a very interesting area to explore. But if you want the specificity when it comes to the DNS simulation, I would suggest reaching out to my colleague, Professor Edward Hawks, who's an expert in this field.
Thank you, Shaun. Just a quick note on that. If you're talking about DNS, so we are not really modeling turbulence chemistry. We still need model for kinetic, but not necessarily turbulence chemistry, which is solving, optical holography scale. The next question is for you, Henry. How did you incorporate machine learning in hydrogen safety? I think this is a more general question, but if you want to provide in your thoughts on that, that would be great.
Sure, this is a great question. So machine learning, as for us, not really computer scientists, are more of a tool. So we're basically using machine learning as a leverage, like I said, to try to expand our data set, try to expand our range of data that we can have. And since we know that this dispersion of the gas or the flow behavior we're looking at is somewhat patterned, correlated with all the parameters we want to tune around, say, your slope angle, your injection rate, whether or not you have ventilation, how much is the ventilation. And the location definitely looking into as well, they are all patterned. And we are trying to use machine learning models and methods to help us gain a bit of a knowledge because what we're doing is we are creating dots and dots and dots in terms of if you are looking at a map or if you are looking at a zigzag puzzle. We are creating some solid puzzle points or pieces there, but in between there's some interlink, there's some correlations that we do not necessarily need to fill in themselves piece by piece by either experiment or by simulation. They are too cost-effective, not too cost-effective. So we know there are patterns existing. So we are using machine learning actually to capture or to try to predict the patterns in between, and we fill in the whole map by connecting the dots. That's the role of machine learning in here. So the first thing, as I said, is trying to expand our data set. Second one, as long as we are confident with the data set that expand to us, we can confidently use the map basically to form up a lookup table or something like that you can sort of imagine or analog to. If we want to look at some certain conditions, we can just, without doing an experiment or without running a simulation, straight away we get a range or we get a sense of where it lands on, how does it look like, probably. But then it gives you an idea whether or not we want to further investigate into this area. If not, then don't waste time, don't waste the resources. But if you are interested in learning into more details, more specific results, then basically pour more effort into it, you will get more accurate results. So that's the role of machine learning in terms of, because our application scenario is hydrogen safety, but I believe this philosophy or this methodology can be applied to much more application scenarios or research fields as well. So that's how.
Thank you very much, Henry. Of course, when it comes to machine learning, it's about your data quality and also, the application we are targeting. But definitely could be a great tool for hydrogen safety. And the last question is for you, Shaun. What is the best oil for hydrogen combustion engine?
I assume the oil here means that the type of fuel that can be best used for the pilot ignition, right? So assuming that my assumptions is right, we are mainly look into the use of diesel to assist with the ignition, because the idea behind that is that we want to retain as much of the characteristic of the existing engine as possible, as such that the modifications required to be made will be the minimal. But if you think about it, it's entirely possible for us to replace the diesel with something that's more friendly, such as biodiesel. This will subsequently reduce the overall carbon emission footprint even lower than just by using diesel fuel itself. I hope that is indeed what you're addressing. I think there's also a question about the mixing of hydrogen with other fuels as well in the webinar chat.
Okay, great.
Right. So I'll just point out that we did recently publish one, I think 3 papers on the topic of mixing hydrogen with methane jet, and we do see some interesting change in terms of the behavior. So in terms of whether that poses a significant safety risk, really depends on your application at the end, but it does change the combustion characteristic, and is indeed important for us to be mindful of that. I'll refer you to some of the papers that we published on that topic.
Okay, thank you very much, Shaun. I think we are already over the time, but I want to appreciate everyone, remind everyone again, the early bird registration is still open. I hope we see you all in Singapore. It's going to be a fantastic event. Thank you for joining across the world. Good morning, good afternoon, good evening. I wish you all the best. And thanks again to our speakers and also the great Aspect team for organizing such a great webinar series. Thank you, everyone.
Thank you all. Thanks, Fatemeh.
Thank you.
Everyone.